Okay, so this is already lecture 17, and first of all, sorry for absence of our previous lecture 16.5. So I was not able to prepare the previous lecture 16.5. So instead of that, please watch my Korean recorded videos already given to you. Okay, so I think that today's lecture is just one intermediate step for our drift diffusion simulator. Um, so why don't you just review our previous lecture? In lecture 16, we just solve only continuity equation, and in order to calculate the continuity equation, we need the electrostatic potential, and that electrostatic potential was calculated from our nonlinear Poisson solver. So everything is quite simple. However, at the end of our lecture 16, we can solve only continuity equation. But eventually we need a coupled system, fully coupled system of having having Poisson equation and continuity equation. So in lecture 16 or 17, we wanted to do that. So just coupling Poisson equation and continuity equation. So that will be the main topic of our today's lecture. So in a sense, it is really straightforward, but when we consider the real implementation, that introduces a few challenges. So we will talk about that practical aspect of our implementation. So although we have homework at the end of our today's lecture, that will be almost identical to the previous homework. So why do I repeat the same homework with you? It is because at the last lecture or last homework, you just solved only continuity equation. And now I'm asking you to solve Poisson equation and continuity equation simultaneously. Of course, since we are considering still equilibrium case, your potential will be exact. Also, your electron density will be exact. So you have already a good solution from the beginning, but anyhow, this coupling is needed to extend your scheme to non-equilibrium cases. So then let's go to our next slide. So our achievement up to now is we can now solve the continuity equation. So however, at the time, potential was fixed. So why don't we just couple Poisson equation and continuity equation? I have already discussed this concept in the previous slide. And today's goal is write a code which can solve the Poisson equation and the continuity equation simultaneously. So already covered in the previous slide. Okay. So now think about our system of coupled equations. So coupled equations here means Poisson equation and also electron continuity equation. Oh, why do you skip whole continuity equation? Of course, if you consider a p-n junction or so-called bipolar devices where both of electrons and holes are important, you have to consider the whole continuity equation. But for a while in this slide, I will just a unipolar device where electron is the only important mobile carrier. Okay, so you can easily extend it to bipolar cases. So we have two equations. The equations mean Poisson equation and electron continuity equation. Those are integrated from xi minus half to xi plus half. So it means that control volume of xi. Then you will have Poisson equation and continuity equation in integrated forms. Okay. Then of course it has its own physical dimension, but why don't you just introduce a scaled version? So scaled version here means that usually I prefer to have the form of divergence of d minus rho equal to 0 as a residue of this Poisson equation. But when you have a look at this form, you can easily find that, oh, this is a little bit scaled. So what is the scaling factor? Here you have 1 over epsilon naught. So you multiply 1 over epsilon naught to the left hand side and right hand side of your Poisson equation. So you have normalize it in this way. Okay. I think that actually this is not the only one. So usually we have to have, for example, if we just integrate it, still we have one integration. I mean that here we have to have even instead. Here this is the form we have to consider, and when we integrate it, then we have difference of d phi over dx evaluated at upper bound and lower bound, and each of them is approximated as phi minus phi divided by delta x. So here we have delta x in principle. However, we don't have delta x in this position. Why? We have multiplied also delta x to the left hand and right hand side. So that's the reason why we have this equation. And in the case of continuity equation, we have a different equation. So this is a prepared form of our Poisson equation, and here we have form of continuity equation. And you know that actually Jn contains many terms like Qn, N, and electric field here, and in our notation, so in one-dimensional case, we can write down in this way. Also Qdn, here we have gradient of n, but that becomes something like this. So when you have a look at this form, here we have no terms related with q times mu sub n. So that is gone, actually, including this minus sign. So that is gone because we have scaled this equation. Okay. So in summary, both of Poisson equation and continuity equation are scaled by multiplying a certain factor to the left hand side and right hand side of each equation. So you have it. And here, once again, originally it should be the electron density evaluated at x sub I plus half, and also this term should be electron density evaluated at x sub I minus half. So, as I mentioned in the previous lecture, this approximation is really a crude approximation. So I just made a linear interpolation of electron density over x-axis. So that is the reason why we have just half of n sub I plus 1 and half of n sub I. Okay, so I repeat again, that is really a crude approximation, and you will see later why it is so crude. But right now we will just work with this approximation. Let's go to the real implementation. So now we have the residual vectors like this one and that one. Elements in the Jacobian matrix is simply given by, so I comma j term is defined as, so our residue vector, it's I term. Also take the partial derivative with respect to our unknown variable vector, and so j term. So we can calculate this one. So if we just apply this concept to our Poisson equation and continuity equation, then we can think about many quantities like r phi round r phi over round, for example phi. Of course, there can be many different phi's, for example phi sub I plus 1, I minus 1. Oh, they will be different. Also, we have another one like round r phi over round. Here, for example, electron density. In principle, we can consider also n sub I plus 1, I minus 1. Of course, we can calculate even I minus 2, but you know that that doesn't exist. You can easily understand. Also, in the case of R sub n, you can think about R sub n and take partial derivative with respect to phi I plus 1, I minus 1. Also, you can think about Rn and partial derivative with respect to electron density at x sub I plus 1 point, or xi point, or xi minus 1 point. So you can easily understand there are 1, 2, 3, 4 cases, and each of them can have 3 different cases. So we can maximally have 12 elements. So in a position, so we have 2 equations, so we can think about 12 entries. So think about the first Poisson equation. This is the Poisson equation. It's a residue function, and we wanted to take first partial derivative with respect to potential. But you know, potential had also position dependency. So phi I plus 1, phi I, and phi I minus 1. So they have different values. For example, if we consider this concept or this quantity phi sub I plus 1, then you can find here we have phi sub I plus 1. So when we take the partial derivative, now we have just the coefficient for it. So now you have this one. And when you go to the next step, partial derivative with respect to phi I, then you can find that this one and this one give you the answer. Oh, I made a real big mistakes, so sorry about that. Oh, here we have minus sign, so please, I have made mistakes in the PDF file, so I will fix it after the session is over. And how about this one? Then finally, when you go to this last one, then you have this, and that. So now you have this different coefficient. So if you have the same permittivity for all over your device, then you will have a certain number, and this is just 2 times of your number, and this is your number. However, as we have discussed in the previous lectures, if we have different materials, then even this term or that term can be different due to different permittivity vector. Okay, so that is quite obvious. And previously, your electron density term, here you have electron density term. This is nothing related with your intrinsic carrier density. So it should be interpreted as electron density evaluated at your position x sub I. So I hope that you can distinguish the intrinsic carrier density and the electron density defined at node I. Previously, when you think about this one, you just cast it into intrinsic carrier density exponential phi over Vt. So, although that is originally electron density term, in the case of a nonlinear Poisson equation, that is also contributing to your phi I term. So, round R phi. However, that was the non-linear Poisson equation only. Now we have just a normal Poisson equation, and also this electron density is now considered as an unknown variable, its own. So instead of considering this exponential dependence, when we take the partial derivative of Poisson equation with respect to electron density, now we have just a coefficient here, of course minus sign. That's it. So, and we have a missing coefficient here, R phi over round n I plus 1. That is identically vanishing. Also, R phi R n I minus 1, that also vanishes identically. Okay, so I think that you can easily understand this one. So I think that you are quite familiar with calculating the Jacobian matrix now, but the reason why I'm just doing it together with you in this lecture is to give you a concrete example of calculating the Jacobian matrix, since our equation is now becomes a coupled equations. Some guy can ask me that question. So when we consider nonlinear Poisson equation, from these electron density terms, we had complicated nonlinear dependencies. For example, that was just modeled as this term. So previously, in the case of nonlinear Poisson equation, that contributed the terms like this, and int and Vt exponential phi I Vt. That was the contribution from the electron density term. But you know that now in the case of a normal Poisson equation, the electrons terms contribution to the Jacobian matrix becomes just a linear one. So this is nothing related with non-linearity. So what happens to our Poisson equation? Why we don't have non-linearity in this case? Let's just consider the same system, the system at equilibrium. So now we consider a system at equilibrium. We can solve it by solving nonlinear Poisson equation, of course, or we can also solve the same system by the combination of normal Poisson equation plus electron continuity equation. So same problem can be tackled by these two different equations or different set of equations, but now we have different contributions to the Jacobian matrix. So why? Previously we had non-linearity, but now we don't have non-linearity. What happens? Where is the non-linearity? So where is the non-linearity? Although we don't have any non-linearity in the Poisson equation, but when we consider Poisson equation and continuity equation, now this continuity equation contains certain non-linearity. So the combined system of Poisson equation and continuity equation also react exactly the same way with nonlinear Poisson equation. Let's go to the continuity equation. Now this is the continuity equation. So here we have the first two terms related with the flux evaluated at upper bound and remaining two terms related with the flux evaluated at lower bound. So in this case, you can find many terms, and let's just consider certain terms. There will be just a repetition, so I will just show you. So round over Rn, continuity equation over round n sub I plus 1. So when we consider n sub I plus 1, now simply speaking, this term does not contribute to this Jacobian entry. Also, this one does not. Why? Why we don't have it? Because this is related with n sub I plus 1. So in this case, let's just consider or calculate it. So partial derivative with respect to n sub I plus 1. Oh, here we have n sub I plus 1. So this term will give you just number half. So this one gives you just number half, and this one is just taken as a coefficient. So you have this number. Also, when you go to the second term, now you have minus Vt, and here you have n sub I plus 1. Oh, now you have minus Vt, and this 1 over delta x comes here. Okay. Then how about the derivative with respect to now phi sub I plus 1? Then in this case, now this one is considered as variable, and all of these coefficient, leading coefficient is appearing here. You can easily find it. And this second term related with diffusion does not have any dependencies on potential, so that does not contribute. So that will be the answer. Point is nonlinearity. We are now talking about where is the nonlinearity. So as you can see here, now your Jacobian matrix is no longer a constant, but this term is constant. Yes, it's not that difficult, but this term really contains nonlinearity. Also, this term means that you have dependence. Your Jacobian element really depends on your solution variable. So when you change your solution variable, your Jacobian matrix will change accordingly. So that reveals the nonlinearity. So simply speaking, this term. Here you have multiplication of electron density and phi. If you consider only the electron density as an unknown variable, then it can be regarded as just a linear term. But you know, now since you have here both of n and phi as unknown variables, now it becomes a non-linear term. Now your Jacobian matrix looks like this. Okay. So simply speaking, previously we had nonlinear Poisson equation. Since the sole equation, nonlinear Poisson equation, should consider the nonlinearity of our system, so that's the reason why the Jacobian matrix contains dependencies on electron density. However, now when we go to the more generalized system like combination of Poisson equation and continuity equation, now Poisson equation just allowed it to its own role calculate the displacement vector according to the charge distribution. So in that case, there is no nonlinearity. But instead of that, this continuity equation takes the role of nonlinearity. Okay? So anyhow, they should perform identically. And so I have already given all of Jacobian matrix component to you. So now implementation can be done straightforwardly. So the only difficulty is arrangement. So when you arrange your unknown variables, please note that at a given position x of I, you have both of phi I and n I. So how can you arrange them? In order to make a full solution vector, maybe there can be two representative ways. One is phi 1, phi 2, and sub phi n. Also, only after all phi values are taken into account. After that, n1, n2, up to n sub the last point. So this is one way construct our unknown variable vector. Another way, alternative way, would be phi 1 and 1, phi 2 and 2, and up to the last phi and last electron density. That can be also another way to arrange our unknown variables. So what is your opinion about them? And here. So which one would be preferred by you? So many of you prefer number one. Okay. So yes. So it is natural extension of our previous lecture. So now you can think about this one. When you just draw the non-zero element of your Jacobian matrix, then what will happen? Say, now think about this one. Now your first upper half is assigned to the electron density. And now the lower half of your unknown vector is assigned to the electron density. Then your Jacobian matrix can be also decomposed into four terms. So four terms here that is related with round R phi. Poisson equation is partially derivative with potential. And this block will have Poisson equation with respect to electron density. Also, you will have electron continuity equation with respect to phi and electron density with respect to electron density. So you can say so. Then I wanted to ask you one question. So you have four different sub-blocks. So you can understand each of them has a size of n by n. So n by n blocks, and therefore there are four n by n matrix, and when arranged in this 2 by 2 way, you will have eventually 2n by 2n global Jacobian matrix. In this case, my question is there any matrix which does not contribute any term? So, for example, is it all zero matrix? This one. Or, my question is here, is it all zero matrix? How about this? This one? Is it zero? Or this one? Zero? Can you expect any of them vanishing as null vector? So none of them vanish. So they are all different from the null matrix. So in this case, so we can think about certain term. For example, think about your second position, x2. Then you are now considering your R phi over R phi 1. You can find that is non-zero. Also, you can find that, so of course that is evaluated at position 2, and phi 2 is non-zero, and phi 2, phi 3, that is also non-zero. Also we have R phi 2 round over and 2, that is not zero. Okay, so what I'm doing right now is think about this pattern. So let's say that this is your second law. then when you just draw non-zero element in this diagram, then you will find this 2 by 2 element, 2 by 2 element from this one, and 2 by 1 element from this one, and 2 by 3 element from this one. And how about this? Where is it? Here you have this term. And here its position is 2, n plus 2, because this n is required because first of all we have to consider all 5. Only after that electron density occurs. So this term is related with n plus 1's column, and this term is related with n plus 2's column. Okay. So now you can understand, if we consider certain width of non-zero element, so now we have 1, 2, 3, 1, 2, 3. After that, here we have n plus 2. So how wide is it? It is m plus 2 wide. That is really wide. And how about the second way? If we assign in our unknown variables in this way, then you will find that these 4 terms will be assigned to, for example, the first one will be assigned to 3, 1 component, and second one becomes 3, 3 component, and this one contribute 3, 5 component. So compared with previously 2, 1, 2, 2, 2, 3. So this 1, 3, 5, 1, 2, 3. This one has widely separated locations of each term. So that is not that good news to these components. However, when you consider the last term, it becomes 3, 4. Then I'm asking you once again, what is the width of a non-zero element? In this case, starting from 1, it ends at 5. So now width becomes just 5. So when we make a comparison between n plus 2 and 5, which one is the smaller number? If we have, for example, 100 grid points along the one-dimensional space, then of course the method number 1 gives you much widely distributed non-zero element. So why do I care about the width of non-zero element? It is only because that really affects the performance of your matrix solver. So in principle, the arrangement of your unknown variable, method 1 and method 2 will give you the same answer. Yes, that's true. But the point is, in order to get the same answer, you need some time. Your matrix solver should do certain numerical job. And in that case, the performance of your numerical solver heavily depends on your arrangement. Okay, and in general, so in general case, they prefer, they means that numerical matrix solvers prefer to narrowly arranged unknown variables. For example, if you have a matrix which is arranged in this way, or in this way, or if you have a matrix arranged in that way, although they represent the same physical quantity and same equations, but if we have to, our matrix solver have to, these two matrices, although expected answer is the same, but it prefer to solve it because it has narrow bandwidth here. This one has really wide bandwidth. So this is a very bad situation for our matrix solver. This one is bad and this one is good. So now I'm asking you the same question again. Then from the viewpoint of bandwidth, matrix is the maximum width of your unknown variables, then which one is preferred? Yes, up to now I have explained that from the viewpoint of a matrix bandwidth, the second method is more efficient than method number 1. Then if we go to the real situation, the real matrix solver or real device simulation, so what is the arrangement? What is your opinion? It is not as clear as my explanation. I just gave you certain discussion where number 2 is far much better than method number 1. So in this sense, I'm quite right. But point is, sometimes people try to solve the same system in this way. For example, they sometimes phi n, and this is round phi, yes, so round n. After divide our Jacobian matrix into several pieces, after that, certain matrix solvers solve only this small matrix, and small matrix, and small matrix. After that, by using the solutions of these small problems, they try to construct the overall solution. So of course, this is not the one-shot property, so they will do certain iterative ways to get the solution for this system. Okay, I mean that if you are trying to just use general matrix solver, then I'm certainly sure that your choice should be this localized expression. However, for some real, how can I say, commercial or widely available implementations, sometimes you can find these implementation. It is because this code use special matrix solver. Its matrix solver prefer to have this method 1. That's the reason why it implements the method 1. So please keep in mind that which one is preferred, that really depends on your matrix solver, because you really wanted to get the efficient implementation. So in order to get the efficient implementation, you wanted to have the optimal arrangement method for your solver. Okay, so since we are now talking about just a general matrix solver, we prefer to have the solution vector in a localized way. So first the x1 variables and x2 variables and up to final point variables. Okay, so time is up. Now I think that I have covered all important point here. Implementation just shown here, you can follow it. And the second half of our lecture material is now discussing about scaling issue. However, I hope that if you are working with Python, for example, you don't have to worry about that because your matrix solver can help in this aspect. Also, in my own research work, I'm using also available matrix solver, and it automatically scale our unknown variables. So I don't care about actually scaling. However, if you are working with MATLAB, unfortunately, MATLAB's implementation about the sparse matrix solver does not provide the capability of scaling. So that's the reason why I have attached the discussion about scaling. And if you are working with MATLAB solver or MATLAB code, then please watch my previous video recorded in Korean, so you can easily find how can you solve it. Okay, then finally, let me just conclude my talk with homework number 15. So in this case, actually this homework number 15 is almost identical with homework number 14. So consider a system at equilibrium. That's it. Difference is, previously I asked you to solve p-n junction, but now let's come back to even simpler system like long and short, our m plus n, m plus structure. That's it. But point is, the difference between 14 and 15 is, previously in 14 you solved only continuity equation, and 15 please consider Poisson equation plus continuity equation. So this is the only difference. The answer will be the same. The effective solution, so final solution after solving this equation, will be the same. But inside it, you have a different implementation. So since this is not that difficult, I just give you a short time. Just due is this Wednesday, but I think that this homework number 15 is particularly easy to you, to most of you, so not that much burden to all of you. Okay, do you have any question? So I want to remind you once again, previously we considered p-n junction, but you have to consider m plus n, m plus structure considered in our previous lecture, and please use different spacings. Please, for example, this one, 600 nanometer long structure is spaced discretized with a spacing of 10 nanometers. So you will have, for example, 61 points. Oh, so in this case, you will have almost 1200 points. So you can easily understand the size of these equations. And the actual number of unknown variables will be doubled because you will now consider electrostatic potential and electron density. Okay, good. Then thank you for watching the video, and see you this Wednesday. Bye.